Gravity and simple harmonic motion, review 5. A position time equation for simple harmonic motion is that. Assume standard SI units. Determine the VT equation. We want to take the derivative, don't we? We can leave that constant right there. The derivative of cosine is the opposite of the sine of that thing. And then we need to use the chain rule to take the time derivative of what's in here. So I think we need to put a pi out like that. What about the acceleration time equation? Well, now we need to differentiate again, don't we? So the acceleration time equation, let's leave our constants out there like we did. Negative 3 pi. All right. When we differentiate sine, we get the cosine of that thing. And then from the chain rule, we again have to take the time derivative of what's in here. So that's going to bring another factor of pi out here. So we got to square that pi. Now, what's the amplitude of this motion? Well, the amplitude is right there, 3. And assuming standard SI units, it would be meters, wouldn't it? 3 meters. How about the angular frequency? What's the angular frequency? To do that, we go back to the pattern for these equations. And the pattern for the position time equation went something like this. The amplitude times the cosine of omega t plus phi. That's why we knew that the amplitude was 3 meters, because in the case of our problem, I'll recopy it, it's 3 cosine pi t. That's how we got the amplitude. But what's the angular frequency? The angular frequency is this omega. And we can see that in our case, phi is 0, and so the angular frequency is equal to pi. Now we should put units on there, radians per second. If you want to change that to a decimal, you can. 3.14 is fine. Radians per second, that's okay. How about the frequency? The equation that we came up with some time ago, one equation, was that the angular frequency is equal to 2 pi times the frequency. So here, if we take the frequency by itself, it's going to be the angular frequency divided by 2 pi. Now let me scoot down here. What did we say the angular frequency was? Pi. The angular frequency is pi. So if we put a pi in the numerator, basically the frequency comes out to be 1/2. I'm going to write it as a decimal. Now what's the unit for frequency? Hertz. 1/2 a hertz. What about the period? The period is the reciprocal of the frequency and vice versa. So that's easy, isn't it? 1 divided by 1/2 is 2. And what's the unit for period? Seconds. How about the maximum speed? Well, we can see that from this velocity equation that's in the upper left here. We know that the maximum value that the sine can have is 1. If that's 1, then the maximum magnitude of the speed is basically 3 times pi. Should put a unit on there. In a case like that, I would probably want to put that as a decimal. Not that it would be wrong if you wrote it like that, but a decimal might be a little bit nicer. 3 times a little bit more than 3, so I calculated 9.4 meters per second. That's the maximum speed that this thing will have. And let's finish by finding the maximum acceleration. A similar line of reasoning holds here. If we look in the upper left here, kind of on the left side of the screen, there's our equation for acceleration. The cosine has a maximum value of 1. Therefore, the maximum that the acceleration can be is 3 pi squared. 3 pi squared. And we definitely want to put units on there, meters per second squared. And if we put a decimal into that, this is about 3. So it's going to be close to 27. And I got 29.6. 29.6 meters per second squared. So that's how you do that. That's how you can go from this position time function for simple harmonic motion and you can calculate a whole bunch of things.